our dehydration column. We've got the desiccant blowing up with a small pump, and we've got the fan blowing inward. We've got bio balls all scattered through here where the desiccant goes onto and gets all the liquid in a good surface area. So the air goes through here, and we've got our sensor up here in this column. And well, if this would work, we'll see that we've got about, what's that reading? There's our flow rate. We don't know if this is accurate though. It's been kind of tricky with us. And here's the gauge coming off of the sensors in here. And then we've got the ambient gauge. And yeah, that's pretty much it. So we would call it a success. Okay, so if my editing skills are okay, then this video should be playing after I show the video of our system running. So I'll go ahead and explain more a little in depth, because we didn't really explain in that video, we just kind of showed it working. But basically how the dehydration column works is it takes the moisture out of the air coming into the system, and that moisture is taken by the desiccant, and that desiccant is circulating, so the moisture goes into the reservoir and it just is absorbed by the desiccant. So the air coming out has a lower relative humidity. And let's see here. So we do have some values from sensors that were on our system, and these values were taken as, we have 68 degrees Fahrenheit at 31% humidity, and that's relative humidity, and that was going in, I should probably abbreviate that, and then we had 75 degrees Fahrenheit at 11% relative humidity going out. So these values were taken using sensors. I don't know if you saw where the sensors were, but this was ambient, just in the room, and this was on the inside of the column. So first we're going to try to figure out the densities of the air that's going in and going out. So first thing we need to do is find the saturation vapor pressure. So you could use the back of the book. It is table A4E for us, because we're in English units. That's on page 964, but I actually found an equation online. It's the Magnus equation, that the one that I have, it accounts for temperature in Fahrenheit, and using that equation with 75 degrees, we found that the saturation vapor pressure was about 0.39. So P sat 0.39 psi, and using that we can find our partial vapor water pressure. So that would be PV, and that is equal to our PS times our relative humidity, and plugging in our values, we get about 0.56 psi, and that is for our PV. So then we can find the partial pressure of the dry air, which we'll notate as PP, and you can just do that by taking the atmosphere pressure and subtracting our PV. So this would be just 14.7 minus 0.56 equals 14.64. So that is our PD, and then moving forward, we're going to have to use ideal gas law. So doing that, we've got the gas constants for dry air and water vapor written up here, and here are the equations that we use for finding the density of the dry air and the density of the vapor. So after plugging in our values that we have here, again, this will be in degrees Rankine that we converted. We find that the density of the dry air is, got it written down somewhere, that would be 0.736, and that is in pound mass feet cubed. And then for the density of the water vapor, we found that to be about 0.00011. That's pound mass per feet cubed as well. Okay, so now we're going to find the density of the two combined. And how we do that is just adding them together. So these two together is total density, and we'll call it dA. That would be 7371, and that's pound mass per feet cubed. Okay, so now we've got the density of the air going out. The method that we use to find the density of the air going in will be the same, just the, we're gonna have a different PSAT, we're gonna have different relative humidity and a different temperature, so that's like definitely gonna change things. But the method is the same and the work is in the paper that I'm throwing at. These we've graduated to finding the humidity ratios of the air going in and the air going out, otherwise known as the absolute humidity, denoted, not really sure what that is, but yeah, it's the humidity ratio. So we do that using this equation from the book, 0.622 times P by the pressure of the atmosphere minus P. Okay, so the PV would be the partial vapor pressure that we found earlier when we were finding our densities. And if we plug in the values that we found, assuming that the pressure is just 14.7 psi standard, we get the ratio plugging our partial water vapor pressure in here for the in and out. We found these earlier whenever we were finding densities. So this would just be the standard pressure, and once we plug it in for the inlet, we get 0.00447 pounds mass vapor per pounds mass dry air, and then for the outlet, we get 0.00236 pounds mass vapor per pounds mass dry air. And it would make sense that the absolute humidity is lower at the outlet because the vapor is getting pulled from the air and it is going into the desiccant. It's not in the air that's exiting anymore. Finding the enthalpy, first we'll do it with some equations. And to find the inlet, we have Hn equals the specific heat capacity of air plus the temperature of the air at the inlet plus the humidity ratio at the inlet. So, and that'll be multiplied by the saturated liquid enthalpy, so Hg. And prior I was using the evaporative enthalpy, which is HFG, and you had corrected me on that. So now we're using Hg instead. And whenever we plug in these values, obviously this was taken from the back of the book. This we found, this we know, this was taken from the back of the book just to be 0.24. And plugging that in, we'll get, for Hn, we get 16.5, and that is BTU, pound mass. And H out, doing the same thing, we get 20.5 BTU, pound mass. Now, so checking the chart rather than running the numbers with these equations, we find that Hn is actually about 21.2 BTU per pound mass, and out would be about 20.4 BTU per pound mass. So moving forward, we're going to stick with these from the chart rather than what we found using these equations, because it wouldn't make sense that the enthalpy going in would be less than the enthalpy going out. This makes more sense. I can't say for sure that I understand why this is wrong, but nevertheless, we're going to stick with these values and assume they're more reliable because this makes sense. All right, now we can find the mass flow rate of the air exiting the system, and we do this by using the density of the air it's exiting, and we calculated that earlier with the cross-sectional area of the pipe and the velocity of the air. So this we measured, and that would be in feet, and this was in feet per second that we measured using the tool. Plugging all those in, we get 0.0509 pounds mass per second. So that's the mass flow rate of the air. So now we're moving on to the mass balance equation, and we do know that the mass flow rate of the air entering the system plus the mass flow rate of the water vapor with it entering the system should be equal to the mass flow rate of the air exiting the system plus the mass flow rate of the air of the water vapor exiting the system. So we can write that as mass flow rate of the air in plus mass flow rate of the water vapor in is equal to the mass flow rate of the air out plus the mass flow rate of the water out. All right, so now we need to calculate these values. Well, because we calculated earlier the mass flow rate of the air with the dry air and the water vapor together exiting the system, we can use that along with the humidity ratios we calculated earlier to find these mass flow rates, all four of them. You can take a look at the equations. It looks something like this. So air in would be equal to mass flow rate of, this is the dry air, this would be mass flow rate of just the air with the water that we calculated earlier, divided by 1 plus humidity ratio in, and that would be equal to 0.0507
and that's pound mass per second. And using the same method, we can calculate all 4 of these values. So I'll go ahead and write them down. Mass flow rate of the water vapor in is equal to 0.0002, and mass flow rate of the dry air out is equal to, this is the mass of the dry air going out, the mass flow rate, 0.0508 pounds mass per second, and then we'll also get the mass of the water vapor, the mass flow rate of the water vapor at the outlet, which we calculated to be equal to 0.00012 pounds water vapor per second. Okay, so if you plug these into this equation, it balances out. The left side is the same as the right side. And another thing we can do with these values is we can actually figure out the amount of the water vapor that was taken by the desiccant. And we do that mass flow rate of the water vapor in minus the mass flow rate of the water vapor out. So if we did that, we would get 0.0001 pounds mass water vapor per second. So that is how much the desiccant is taken out there. Okay, so now moving on to the energy balance equation. We know that the heat added to the system plus the air going through the system, that includes the water vapor and the dry air, as a mass flow rate, which we already calculated earlier, and we know that's constant through the system. Mass flow rate of air plus, or well, actually that would be multiplied by the enthalpy of air going in. We know that should be equal to the heat leaving the system plus m air, because that's constant, but it's got a different enthalpy when it leaves, H out. Here's our mass balance equation. Okay, so we're not adding any heat to the system, so we know that this is 0, and we know the mass flow rate of the air. We calculated that at the exit with our tool and measuring the diameter of the pipe where the air exits and using the density of the air. So this is constant to the system, and we already calculated the enthalpy in and the enthalpy out earlier. So the only thing we don't know is the heat that's leaving the system. And you had actually said that you wanted the amount of heat that was going into the desiccant, which would be the heat leaving the system. So we can rearrange this and find the heat leaving the system into the desiccant and assume all other heat dissipating is negligible. So Q out, in this case, would be equal to M out, or M air times H out minus M air times H in. Okay, and once we plug all this in, we will get an answer in units of BTUs per second, so heat per unit time, and that ends up being about 0.037 BTU per second, meaning that this is the amount of heat that is going into the desiccant, into the reservoir outside of those. So this is how much our desiccant is heating up. And unfortunately, we can't find the temperature change of the desiccant, because to do that, if we wanted to, we would have to use delta T equals the heat multiplied by mass flow rate of the desiccant times the specific heat capacity of the desiccant. Unfortunately, we don't know the mass flow rate of the desiccant because it was never measured by us, and we also do not know the specific heat capacity of the desiccant. If we had paid attention to the amount of salt that we had put into the water and known the mixture, we could have possibly found this, and we didn't though. So we are unable to find the delta T, but we do know that this is the amount of heat entering the system per unit time. So with that, all that being said, I do believe that this all makes sense. And also again, if you plug in the values here, our energy balance equation statement is true. Left side equals the right side, with n being 0. So thank you for watching.